its semigroup, and that's its integral kernel. And so if you integrate from negative to plus infinity, this is the solution of this equation for that particular operator in one dimension. Of course, you could do it in n dimensions in the same way. The only difference in n dimensions would be n over 2 if here you would integrate over I. That's the only difference, believe it or not. So if instead of this you take the Laplacian on In, then everything goes exactly like this, and the only difference is that n. And of course, this is understood as the square of the vector in In, and that will give you the solution of the heat equation in n dimensions. So that's why you need operator theory, why you need Fourier transform, and so on. Depending on the shape of on the form of the operator, instead of Fourier transform, you may need some other transform, like Milne transform, Bessel transform, some other. The point of it is that you apply operator, well, here's an arbitrary function, and you replace it as a linear combination, some very specific function, in this case, exponentials, and an operator with constant coefficients acts on that trivially by multiplication. Like take derivative, it's multiplication by IP. Okay, and so if you have some other operator, then you choose different basis functions on which it acts by multiplication. Well, let me give you an example. Suppose you have an operator like this x dx. And it would be a bad idea to use Fourier. I mean, it wouldn't work. But you need to find a function on which this operator acts by multiplication. Well, you probably know this function very well. You just don't realize it. If you look at, say, x to the s, just power instead of exponential. You take this x d of that. What is it? Well, it is x, right? The derivative. Well, derivative is s, x to s minus 1. So if you multiply, you get s, x to the s. So you just multiplication by s, which is, again, multiplication. So if you have a function, f of x, and then if you can write it as some kind of an integral over, well, let's say x to the s and then some function of s, then that operator would act on this just by multiplication. And so if you take, say, like e to TL, then here you would just get e to TX. I mean, that's all you will get. And then the only thing you need is to compute the integral over s. That's called the Milne transform. Okay, well, I'm not going to do, I'm just saying that the type of the integral transform you use depends on the form of the operator. The idea is that you have a PDE, right? Well, say of that form. You have an operator, say partial differential operator, L. And then you do an integral transform. And here you get an algebraic equation. Well, let's say partial differential equation, and here you get algebraic equation, because different differential operators are replaced by multiplication operators. So you solve it easily, right? So here, well, let's just say you have this here. Here you'll have, well, let me put heads on everything. So the solution of that is, of course, that, and once you have this, then you do the inverse transform, and that gives you the solution of this problem. So instead of doing it like this, which is difficult, you go this way. You transform it, solve it, do the inverse. Okay? Of course, it will work if the type of the integral transform is appropriate to the form of the operator. Okay, and another thing I want to tell you, because the next chapter is on Fourier transform. Well, there is one thing. I mentioned when we discussed this with Andrew, I think it would be useful to all of you. This is the notion of pseudo-differential operators, which are more general than differential operators. So they're not exactly differential operators. Sometimes they call, which stands for pseudo differential operators. Well, first let me explain what a symbol is. And I'm going to do it in one dimension, but it's the same thing you could do in n dimensions. Well, let's say you have an operator in one dimension, a differential operator that looks like this. Let's say a of x, say second order. Something like this, okay? So that's a second order operator. Then what is its symbol? Well, the symbol is the following. So the symbol of the operator L depends on x, and it depends on, well, let's call it P. Like this is coordinate and this is momentum. And this is obtained by taking that operator and acting on E of I, Px, and then killing that exponential. So if you do this, then the net result is that you replace the derivatives by IP. That's exactly how it acts on the Fourier transform. So you basically get negative a to the x p squared plus I, well, let's see, b of x I p plus c. So this is called the symbol of the operator L. The part with the highest derivative, that's called the principal symbol. That determines the type of the equation, that determines everything about the principal symbol. The lower the term don't matter that much. Okay? So like ellipticity, hyperbolicity, whatever, the properties of the qualitative properties of the type of the equation depend on that, like in particular in multiple dimensions. So that's a symbol of a differential operator. Well, look how does, let's say you pick an arbitrary function and you act on this function by that operator. What will happen? Well, you have L, and then you expand it in the Fourier series like that, and then you add L on this exponential, right? And you get the symbol. You get the symbol times the same exponential. So, in other words, the action is equal to, well, this exponential times the symbol. So that's a very useful formula. It tells you how the differential operator acts on any function. You just multiply it by its symbol, even if it has non-constant coefficients. This is non-constant coefficients, right? Just arbitrary operator. You just act on it, and then, well, now you have to compute this integral. And it will tell you what the action of it is. So, notice that this is a polynomial. Right? So this is a polynomial of degree, well, in this case 2, which is the order of the operator. So the order of the operator L is the degree of its symbol. Oops. So, well, if you don't like partial derivatives, you may not write them at all. Just give me the symbol, give me that expression. That describes completely the action of the operator by this formula. And of course, given that, I could easily reconstruct this just by replacing P with ID, and that's it. Right? So, usually, well, if you go to analysis of PDEs, you'll see that everybody writes symbols. They don't write differential operators because, well, it's the same thing. But once you have a symbol, well, actually, if you compute this integral, then, in fact, you'll get this a times the second derivative plus b and so on. You can actually compute it. You'll get the same thing. The point is that now you can look at this expression and say, well, we don't care what this sigma is. So it doesn't have to be a polynomial. It's just some function of x and p. So let's define an operator. Well, let me call it, let's say A on F. And I'm going to define it like this. Well, let's call it